The last parent function we're going to revisit is f of x equals 1 over x. We haven't talked much about this function, but it is called the reciprocal function, and it is something that we explore after we learn about rational functions. So we did our unit on add, subtract, multiply, divide, solve with rational functions. Now let's talk about what if we were to graph a rational function, or in this case called the reciprocal function, right? This function is very interesting in terms of its domain and range and what it looks like in the coordinate plane. So if we were to just plot some points to get an idea of what it looks like, let's plug in some values. So if I plug in -1 for x, I'm going to get -1. If I plug in -1/2, so that's essentially 1 divided by -1/2. Your calculator can help you, but if you just use your mental math, this is 1, so dividing by a fraction means multiplying by the reciprocal. That turns out to be -2. If I do 1 divided by -1/4, that turns out to be 1 times -4 over 1, which is -4. If I plug in 0, division by 0 is undefined. So this is undefined, and what we have just done is we have determined a value that is not in the domain of the reciprocal function. So now we know when we go to write the domain, we may not include 0 in the domain. These are just the positive values of the one we just did. So 1/4 is going to be a +4, 1/2 is going to be 2, and 1 is going to be 1. All right, so let's plot that, okay? So -1, -1, -1/2, -2, -1/4, -4, okay? I didn't go the other way. I didn't plug in -2, -3, -4. But if I do, I'm going to be getting values that are smaller and smaller. And so in the third quadrant, we end up with what is called a branch. And this is what the branch looks like. And again, you can throw this into Desmos and get a nice picture of it too. The 1 over x graph is symmetrical within the coordinate plane. So we're going to get that same type of branch in the first quadrant. So again, we've got 1, 1, right? We've got 1/4, 4, 1/2, 2. And then again, if we plug in 2, we're going to get a half. 3, we're going to get a third, a fourth. And so you see that the second branch is symmetrical. We call this symmetrical through the origin. Symmetry through the origin, okay? These are called 2 branches, 2 parts. The actual parent function is separated. It is not continuous, and that is because of our undefined value in the domain. So let's go ahead and write that domain. We know we can have negative numbers. We know we can go all the way up to 0, but we can't include it. Well, I should be writing this down here. So -infinity to 0, union 0 to infinity. So we can include all of the values, okay? But we cannot include 0. Same thing for the range. All numbers will come out except 0. All right, now it's time to revisit something called end behavior. Okay, the end behavior was the behavior of the function as x got really big or as x got really small. All right, and that's interesting for the reciprocal function. So there are many topics you will learn more about end behavior in regards to the reciprocal function, but we're going to talk about the end behavior as we did at the beginning of the year. Keep in mind that as you move through higher level math classes, you notice that because the branches have 2 ends, we can talk about different approaches. So what we did was, as x approaches infinity, we said, hey, what's happening to the function, right? But notice that there are two arrows in that first branch in the first quadrant. So we could also talk about as the function, as you approach the function from the right, as it approaches the value 0, what happens to it? Again, that's for future math courses. For this one, as x approaches infinity, f of x is approaching, right, positive infinity, right? But it's also approaching the line y equals 0. Because this, let me make it a little bit thicker. This is a line on this parent function that is called an asymptote. Y equals 0 is an asymptote for this function. What does that mean? An asymptote is a line on a parent function that represents what the function approaches at its end behavior. So it's approaching the line y equals 0. It is approaching the x-axis. If you plug in 100 for x into the parent function, you're going to get 1 over 100. That's super small. Think about how close that is to the x-axis, okay? And as x approaches negative infinity, f of x is going to approach, let's think about that, negative infinity. It's also approaching the line y equals 0, but from the other side. Right? And so we have an asymptote, but we also have another asymptote because it says, what are the asymptotes? Well, we know that one of them is the line y equals 0. That's this one right here. But look at the graph as x approaches 0 on either side. So as it approaches 0 from the right and as it approaches 0 from the left, we also have an asymptote that is the line x equals 0. Okay, so these are called asymptotes. So x equals 0 and y equals 0. Those are identified as the asymptotes. Okay, so let's try examples 1 and 2, and then you can practice some. Okay, identify the asymptotes, domain, and range of the function. So here's our parent function, the reciprocal function. Okay, you can tell it's been moved, right? Can you visualize the asymptotes? It's helpful if you try to actually draw them in. I think there's one right here because that's where there's a break in your branches. I also think there's one right here. So you can visualize where your branches are broken, okay? So the first one is, okay, no, let's look at our graph here, right? Because according to those boxes, this is 5, right? That means this is 2.5. So x equals 2.5 is one asymptote, and then y equals 0 is the other one. Okay, so this one is the vertical, and this one is the horizontal. Okay, domain and range, right? Well, actually, that would have to be 2, right? Actually, that doesn't make any sense because if you look in the denominator there, so let's take a look at this. This is not really a great example. This is f of x equals 3 over x minus 2. But if you look at the graph, I guess it's at 2. So I'm going to go back and correct myself there. This should be x equals 2. And the reason I know that is because that's not in the domain, right? It just was, the appearance on the graph looked like it was at 2.5. But when I actually look at the function, I know that if I plug in 0 for x, it's going to make the denominator equal to 0, and therefore it is not in the domain. So negative infinity to 2, union 2 to infinity. And then my range, negative infinity to 0, union 0 to infinity, okay? Because we know we can't have 0, because look, there's a pink line through the y-axis, or excuse me, through the x-axis, so the y value is never 0. Now take note at the asymptotes. So I'm going to change my color for a minute here. I want you to look at the asymptotes, and then I want you to look at the domain and range and see if you can see the connection there. There is a vertical asymptote at x equals 2. You cannot have 2 for a value of x, and look how that shows up in the domain. Y equals 0 is your horizontal. The y value is never 0. Look where that shows up in the range. Notice it's excluded from the range. Okay, let's do one more, and let's pay attention to the equation. So I'm looking at this equation. I know that x cannot be negative 4, right? Because if x is negative 4, it produces a 0 in the denominator. So this one seems clearer. So I'm going to go ahead and draw that in, okay? And then it also went down 2. There we go. All right. So my asymptotes are x equals negative 4, y equals negative 2. Now, let's make that connection to the domain and range. So my domain, negative infinity to negative 4, union negative 4 to infinity. Okay, we cannot have negative 4 in the domain. Range, we're not going to have negative 2 in the range.